Ladies and gentlemen, thank you for attending to my academic report. My name is Haoyang from School of Electronics and Information Engineering of Harbin Institute of Technology. The topic of my report is equal proportional probability caching policy for a heterogeneous network based on stochastic geometry theory. My report consists of 5 parts, respectively are introduction, system model, caching policies and performance analysis, numerical results, and summary. The first part is introduction. With the explosive growth of mobile data services, the usage demand for high-speed data streams is rapidly growing. However, when the user tends to use conventional backhaul network, they would face many disadvantages like high time delay, low transmission rate. And for the network side, the load of the core network would be very high. To solve this problem, the recent research tends to combine caching technology with heterogeneous network. When the heterogeneous network is equipped with cache memories, the users would benefit from large coverage, low backhauling pressure, and high efficiency of the network. The second part is system model. Consider the downlink transmission scenario of HeadNet with cache-enabled small cell base stations and backhaul link deployed macro base stations as shown in Figure 1. The two-dimensional spatial distribution of the MBSS and SBSS follows two independent Poisson point processes denoted by phi-m and phi-s respectively, which represent the spatial location sets of MBSS and SBSS. The density values of MBS, SBS are lambda m and lambda s respectively. Since we only consider the performance from the user side, we assume the spectrum allocation of both SBSS and MBSS are the same. The transmit power of MBS, SBS is denoted by PM and PS respectively. The radian of service area for each SBS is denoted by Rmax. We assume that each user requests the content from a library which contains n files, and the cache space of each SBS is M, where each file is assumed to follow unit size. The files are indexed according to their popularity, ranking from the most popular to the least popular. The popularity of each file being requested follows the zip distribution, according to which the requesting probability of the highest popular file is shown as Formula 1, where delta is the skew parameter of the popularity of different files. As delta grows larger, the gap between the high popularity files and the low popularity files becomes larger. We assume each SBS selects the files to be cached independently. The probability of the highest popular file to be cached on SBS is denoted as Qi. Since each file follows the unit size, the average space occupied by the highest popular file is Qi. Thus, the summation of Qi is shown as Formula 2. The most commonly used caching policies are uniform caching policy and popularity-based caching policy, where UCP makes SBS cache each file with equal probability and PCP only cache the most n popular files, denoted as Formula 3 and Formula 4. The downlink signal to interference plus noise ratio for a typical user requesting the highest file when associating with SBS or MBS are shown as Formula 5 and Formula 6, where HSI and HM are the equivalent channel power from the associated SBS or MBS. We assume both SBS to user and MBS to user channels are modeled as Rayleigh fading channel. Thus, both HSI and HM follow the expositional distribution with unit mean. RSI is the distance between the typical user and the nearest SBS which caches the ICE file. RM is the distance between the typical user and the nearest MBS. Alpha is the path loss exponent. For the ease of the calculation below, the value of alpha is set to 4. The interference generating to the typical user which is associating with SBS is ISI. The interference to the typical user associating with MBS is IMI. Since the head nets are usually interference limited, we neglect the effect caused by the additive noise. The third part is caching policies and performance analysis. In this section, we propose an equal proportional probability caching policy and a connection strategy to increase the usage ratio of SBS. Then we use the outage probability as the performance metric to analyze the validity of the system. In this section, we start with equal proportional probability caching policy. When using UCP, if the request probability gap between each file is large, the high-ranking files possess the same cache probability as others. On the contrary, when using PCP, if the request probability gap between each file is little, the low-ranking files still won't be cached, although the gap of the requesting probability between the low-ranking files and the high-ranking files is not large, resulting in the low cache hit probability. The primary reason of this problem is the cache probability of a typical file cannot match its corresponding request probability. To solve this problem, the equal proportional probability caching policy is proposed. With this policy, the first popular file is most likely to be cached. Then Qi is equally proportional to Qi-1 with proportionality factor d. So if we set Q1 as a function of sliding parameter beta, which makes Q1 slide from m divided n to 1, according to formula 2, the summation of the average space is shown as formula 7, where step A follows the summation formula of geometric sequence. By solving this nth degree polynomial equation with dichotomy, we can obtain a unique solution of D within 0 to 1. Then we can obtain the caching probability of each file. The above is the achievement method of EPCP. Then we will introduce SBS priority connecting strategy. To release the load of the backhaul link, we use the SBS priority connecting strategy. When a typical user requests the ICE file, it firstly searches and associates with the nearest SBS, which caches the ICE file within Rmax. If there is no SBS which satisfies the requirement, the nearest MBS would fulfill the request and obtain the requested file from the core network through a backhaul link. By this strategy, the backhaul link would be occupied only when the SBS cannot provide service, resulting in link pressure to be released. The probability of the user associating with SBS tire when requesting the ICE file is denoted as PSI, as shown in formula 8, which is equivalent with the probability that there is at least no SBS within the circle area centered on the typical user of radius Rmax. When a typical user connects with SBS tire, the probability density function of user to SBS distance is shown as formula 9. Similar to formula 9, when a typical user connects with MBS tire, the probability density function of user to MBS distance is shown as formula 10. Then we will introduce outage probability. We use average outage probability as the performance metric to reflect the quality of service, which is the average probability that the downlink channel SNR be inferior to the given threshold gamma, which is shown as formula 11, where P out Si represents the outage probability for SBS connected user when requesting the ICE file, which is shown as formula 12, where these three parts respectively represent the Laplace transform of their probability density function. That's because these three random variables are independent of each other, so the probability density function of their summation is the convolution. Then we get formula 13, where step A is from HM follows the exponential distribution with unit mean. Step B follows the theorem of convolution. The Laplace transform of the first part of formula 13 is shown as formula 14, where step A is from HM follows the exponential distribution with unit mean. Step B is from the probability generating function of Poisson point process, and step C is from the assumption that the path loss parameter alpha equals to 4. Similar to formula 14, the second part and the third part are shown as formula 15 and formula 16. Similar to formula 12, the outage probability of the typical user request when associating with MBS is shown as formula 17, where the three parts of the formula 17 are shown as formula 18, 19, and 20. Then we come to numerical results. In this section, we present the numerical analysis of the outage probability and verify the analysis results with 10,000 time Monte Carlo simulations of a 5 kilometers multiple 5 kilometers size network. Gamma is 20 dBm, PM is 50 dBm, PS is 30 dBm, M equals to 70, N equals to 100, Rmax equals to 30 meters, lambda M equals to 10 per kilometer. Figure 2 shows the average outage probability for different caching policies as the function of skew parameter delta. We can see the results of the performance analysis match the simulation results, the red line. The average outage probability of EPPCP is lower than others at the range of 0.2 to 1, where there is no cache deployed on SBS. From formula 12, we have P out Si equals to 1, since the typical user associates with the nearest MBS regardless of the file it requests, and the interference produced by SBS keep unchanged with I. The SINR does not change with delta, resulting in the average outage probability keeps stable. When using UCP, the outage probability when requesting the ICE file keeps unchanged, resulting in the average outage probability stabilized with delta. Since the requesting probability gap between the high-ranking files and the low-ranking files is not large between 0 to 1, the EPPCP has lower Pout Si when requesting low-ranking files than PCP, resulting in lower average outage probability. On the contrary, the average outage probability of EPPCP is higher than UCP between 0 to 0.2 for the same reason. Since delta has the typical value of 0.5 to 1, EPPCP would be a better option than other caching policies. Figure 3 shows the average outage probability as the function of lambda s. We find that for different caching policies, the average outage probability firstly grows larger. That's because when lambda s equals to 0, there is no interference produced by SBS, which is the main part of the total interference, resulting in large SINR. As lambda s grows larger, the average outage probability tends to fall since the average distance to the associating SBS gets shorter, resulting in larger signal-to-signal power received and larger SINR. Thus, when we build ultra-dense HETnet with cache-enabled SPS, we would sacrifice a little bit of average outage probability in exchange for the release of backhaul link pressure and lower time delay. Unlike the above, when there is no cache deployed, the average outage probability would only rise with lambda s since there is only interference increasing caused by higher dense SPS. Figure 4 shows the average outage probability as the function of beta when using EPPCP. We find that the average outage probability becomes smaller with beta, which means the performance becomes better with a more skilled caching policy. We applied an equal proportional probability caching policy with SBS priority connecting strategy on cache-enabled heterogeneous cellular network. By modeling the spatial distribution of the BS as two independent poison point processes, we obtained the average outage probability for a typical user's request. The simulation results showed that the proposed policy resulted in lower AOP than the classical policies when delta is in the interval 0.2 to 1. In addition, we investigated the relationship between the density of SPS and AOP, which concluded that the high-dense SPS would sacrifice a little bit AOP in exchange for the release of backhaul link and lower time delay. Lastly, we investigated the relationship between the sliding parameter and AOP, which concluded the performance becomes better with a more skilled caching policy. This paper highlights that the new caching policy performs better than the conventional policies under cache-enabled HETnets, underscoring the fact that using high-dense network in conjunction with a more skilled caching policy would obtain a better system performance. Thank you for your attention to my report. Below is my email address.